Okay, well, maybe we should just get started. And so it's a pleasure to introduce Partha Dey. He's speaking from the University of Illinois at Urbana-Champaign, and he'll be talking about the Curie-Weiss model under LP constraint. So welcome. Please begin, Partha.
Okay. Yeah, first of all, thank you, Sundar, for the invitation. So this is a joint work with Daesung Kim, who is right now a postdoc at Georgia Tech. And this should be up on archive like in a couple of weeks. So, so let me kind of start with the toy Ising model on complete graph, which is well known and probably all of you know that, but I'll just kind of recap. So here we have a complete graph on n vertices, and then every vertex has a spin taking values in plus minus 1. So we have a n tuple. So this is the spin configuration space. And then we have the corresponding Ising Hamiltonian, which is sum over all possible edges. Look at the product of the spins, and this 1 over n is needed because the degree is n. And then one can consider the Ising measure or the Gibbs measure as inverse temperature beta, proportional to e to the power beta times this 1 over n summation sigma is sigma j. So here the standard one is this Gn beta is the partition function, which is the which makes it a valid probability measure. Now this is a kind of a very well studied model. So this is also known as the Curie-Weiss model or Ising Curie-Weiss model because of this plus minus 1 spins. Now, so this model is well studied. Its kind of its properties are well understood. So for this model, one can actually prove a phase transition as the temperature or the inverse temperature beta changes. And the order parameter here is the magnetization, which is the average spin. And in this model, the critical temperature or critical inverse temperature is beta c is equal to 1. And the phase transition happens in the following fashion. It's like if you take beta less than beta c. Now, when beta equal to 0, then this is just the uniform model, the uniform spin on plus minus 1 to the power n. So when beta less than beta c, the model behaves almost like beta equal to 0 or infinite temperature, in the sense that this average spin or the magnetization is concentrated around 0. And so, moreover, if we multiply m sigma by root n, it has an asymptotic normal distribution with mean 0, but the variance now depends on beta. So if our beta is equal to 0, then it's normal 0, 1, just usual central limit theorem. But for beta bigger than 0, less than beta c, one can prove normal. And you can see the variance is diverging to infinity when beta goes to beta c. And now, now if beta is bigger than beta c, in this case, the magnetization is not concentrated at 0. It's concentrated at with probability half and half at some non-trivial point, which can be obtained by looking at the unique solution of this equation x equal to hyperbole beta x. And this indeed has 3 solutions: 0 and plus minus x star. And the magnetization is concentrated at the plus minus x star. And it's also well known that if we look at the critical behavior exactly at beta equal to 1, then we don't have Gaussian limit. We can see that the variance is exploding. But if we scale by something smaller instead of n to the power half, if we scale by n to the power 1/4, then we have a limiting distribution. And the density is a non-Gaussian density, e to the power minus x to the power 4 multiplied by some constant. Okay, so this is kind of a toy and very well studied model. So what's new? So we considered actually the following model. So instead of looking at the spins taking like unconstrained plus minus 1, so we fix some p, some real number p bigger than 0, and we look at the following configuration space. So this is the set of all spins. So sigma is in Rn such that the average of this whole to the power p, so mod sigma to the power p is equal to 1, or the sum is equal to n. So one can think about like if p is equal to infinity, this will give us the plus minus 1, the classical Curie-Weiss model. Now, once we have this one, so here this is continuous. This is a continuous space. So one can think of this as the surface of this LP ball, with appropriate radius. Now one can consider a Curie-Weiss model on this configuration space. So that means that we have the same Hamiltonian, just take a sigma from this space, look at the Hn sigma, which is this 1 over n summation sigma I sigma j multiplied by beta. And now we have the corresponding uniform measure on the surface. And one can also define the corresponding partition function to make it a valid density. And so now the question is, okay, so for p equal to infinity, we know what is the behavior here. So the question is, do you see the same behavior for all p positive? So the main question is like, okay, so first of all, how do you analyze the model? Because here we have more constraint because the spins are constant to lie on the surface of the LP ball. And so the next question is like, do you have a similar phase transition at all p bigger than 0? So in the sense that, is there any critical inverse temperature beta c such that if beta is less than beta c, the behavior is like beta equal to 0, or the magnetization is concentrated at 0, whereas if beta is bigger than beta c, there is something else happening. The magnetization is not concentrated on 0. And similarly, do we see a Gaussian fluctuation if beta is less than beta c? And do we have some kind of universality at the critical temperature? So like, for example, at beta equal to 1, for the classical case, we have this n to the power 1/4 scaling, and the limiting distribution is e to the power minus x to the power 4, whether we get a similar kind of behavior. So the question is like, okay, so how to analyze this highly dependent model where it's like a more of a constant model? Now, before going to the answer, so let me kind of simplify this model, and which will also give us a more general model. Now, this is a well-known result. So suppose we look at the following probability density on R, proportional to e to the power minus x to the power p over p with an absolute value. So this is a symmetric density. And one can see that Cp is explicitly computable, which makes it a valid density. And now if I take x1, x2, xn, IID random variable from this density, then if we scale the vector to make sure that the vector now belongs to that sigma np, then this scaled vector is uniformly distributed on that on this omega np ball. And if p is equal to 2, this is exactly the Gaussian distribution, e to the power minus x square over 2. And this is the kind of corresponds to the case that if you look at a uniform point on the n-dimensional sphere, L2 sphere, actually one can look at the distribution by taking IID Gaussian and scale it to make sure that the L2 norm is equal to constant. So this is a general version. And much more is known, but now once this is known, so that means we can actually simplify the model, and instead of restricting on the surface of the sphere, we can convert it to on Rn, but then each of the xi should be replaced by the scaled version. So remember that when to get a uniform measure, we have to scale xi by the corresponding norm. So this is not the usual LP norm, this is just the average LP norm. 1 over n is there, but otherwise it's kind of the same. So we have to kind of do the similar kind of scaling. And using this, we can convert this problem to a problem on Rn instead of the sphere, on the surface of the sphere. But now the problem is that this becomes nonlinear. So this becomes not only on this kind of sum structure, but there's a ratio structure. And p is arbitrary, p is bigger than 0. So there is no kind of non-trivial, there is no trivial way to kind of remove this restriction. Now here, this rho p is coming from this rho p, which is proportional to e to the power minus mod x to the power p over p, but we don't need to take this rho p. We can just replace it by any symmetric distribution. We don't even need any density. So we can replace this rho p dx by any symmetric distribution. So symmetric just to make sure that we have this appropriate sign plus minus 1 sign symmetry. And also if p is bigger than or equal to 1, actually we don't even need any moment assumption. Like rho p can have infinite mean because of this self-scaled behavior. This is always scaled. So these quantities are actually always, this quantity is always bounded and this quantity is always negative. So for example, if p is bigger than or equal to 2, so both of these are bounded. And if p is bigger than or equal to 1, then this is of course bounded. And this is also something which kind of stays bounded. Now, if one removes this restriction, so this denominator, just keeping the usual Curie-Weiss model with this generalized product of d rho x, then one actually gets the generalized Curie-Weiss model. So where the classical Curie-Weiss model is when rho is symmetric plus minus 1 with probability half and half, but one can replace it by rho and one can get the generalized Curie-Weiss model. But in that case, we need some restriction on rho, because if we don't have this scaling, then we need restriction to make sure that this is well defined. Otherwise, this will explode. Actually, we need a sub-Gaussian tail decay when we don't have this restriction. Okay. Now, okay, so why we are kind of looking at this model? So the motivation actually came from many different things. So let me kind of give you some related results. So if we have sub-Gaussian tail decay for rho, and this is really needed for ZNP, for the partition function to make sense, otherwise it will be infinity. So under this model, Ellis and Newman, so they proved like long time ago that there is a phase transition at beta c, which is 1 over the variance. So in the classical case, the variance of symmetric plus minus 1 is 1. So you get that phase transition at 1. And there is a similar Gaussian and behavior for beta less than beta c, and critical behavior at beta equal to beta c, but it might depend on rho, the critical behavior, and then something different happens for beta bigger than beta c. So this is the classical but generalized Curie-Weiss model. Now, if we consider p equal to 2, which is the case where there's a scaling, but this quantity is just 1 over n summation xi squared. So that actually corresponds to the self-organized critical Curie-Weiss critical model introduced in Sarf and Gorny in 2016. And they also showed that if we assume a sub-Gaussian tail, so sub-Gaussian tail means the tail is decaying like e to the power minus some constant times t square. So mod x bigger than t is decaying faster than Gaussian. So there also the phase transition happens at beta c equal to 1. Now you might say, like, why is 1 here? Why not the 1 over the variance? The reason is that you can see that here the variance does not really matter because it's scale invariant. Like if I scale xi by any constant, it does not matter. It will be the same. So I can always assume my variance is 1 if we have appropriate assumption on the tail decay. So that's why the critical temperature here is, or inverse temperature is equal to 1. So the variance does not appear here. Okay, so that means at infinity, we get this critical behavior, 1 over the variance. So in particular for the Curie-Weiss case, we get 1. Here also we get beta c equal to 1, but this 1 is because it's invariant under scaling. But one thing to notice is that we still need a sub-Gaussian tail behavior here for the analysis. Now, a detailed behavior is known at the critical beta c. So n to the power 1/4 times the magnetization has a similar kind of density, e to the power minus x to the power 4. And there are many results, and also there are extensions. Gorny actually did it for the Gaussian, and then using Hubbard-Stratonovich, Gorny, and Varadhan, they have a proof at criticality. And then Florian also, it should be an L, has results on some linear and on the planar Ising model on this kind of cell scale. Now, this is also connected to a self-normalized process, because you can see that because of this self-normalization, we don't need any assumption on this xi. So there is a self-normalized behavior. And there's a good book just called Self-Normalized Process by Victor de la Pena and Lai and Shao. I mean, they have like a lot of results here. Now, this is also, so what I'm looking at is the non-disordered model. There is no randomness other than this Gibbs measure. So because it's like a deterministic measure, and we are looking at the behavior of a configuration from there. But one can also consider a disordered model, or the spin glass model, where instead of summation sigma I sigma j, one can put some normal random variable. So summation some gij sigma I sigma j. And that model is actually known as the LP-Gothendick spin glass model. And there also the limiting free energy, or 1 over n log-partition function, is known, and the solution is given by some Parisi formula. But in that case, the scaling behavior, the fluctuation is unknown. Now, so here we are looking at kind of a nonlinear model on a constant surface. Now, if we just look at the uniform behavior, so beta equal to 0, so there is no kind of interaction, it's just beta equal to 0, but we are focusing on the intersection of, say, some high dimensional symmetric convex bodies. So here we are focusing on just one summation mod x to the power p equal to n, but one can look at multiple of them. And in that case, it also shows a phase transition. So in particular, if you have intersection of 2, 3, or more, so Saurabh actually, Chatterjee, he proved the intersection for L2 and L4 ball, and then now in 2020, he proved for arbitrary finitely many, this kind of LP1, LP2 finitely many balls. And in all these cases, the typical point, the distribution of typical point actually goes through a phase transition. So depending on the value of the summation mod x I to the power p equal to something, one can show a different kind of behavior. So either all points are IID, or there is some point which behaves differently from the other points. Now, so here we are just looking at constant model on only one sphere, one LP sphere, but one can also try to look at the similar model on intersection of multiple high dimensional bodies, but that's a future question. Okay, now, so what is the main result? So the first one is try to understand the behavior of the log-partition function. So here I'm just using a different, instead of z, script z is basically the same, but there is a small change. So here the first thing is that what we need is that x should not have lot of mass near 0. So this is a negative quantity. So for some alpha positive, we have 1 over x to the power alpha finite moment. So one can think about like near 0, for example, if near 0 we have constant density, like positive density or no mass, this is fine. So that's the assumption we need. So first of all, of course, we need x to be symmetric. So here I'm assuming x is from rho. So remember, rho is a symmetric measure. And we need this kind of a minimal assumption that 1 over x to the power some alpha is finite. And let's define this expectation, which is expectation of e to the power ux minus vx to the power p mod x to the power p. Now, in our case, v will always be negative and p will be bigger than 1. So this quantity will always make sense as long as v is negative, because mod x to the power p will always dominate x. So as long as p is bigger than 1, this function is well defined as long as v is negative. So the first result is that, okay, so if we look at the limiting free energy, so this is 1 over n, the log-partition function, one actually can show that, okay, this has a variational formula in terms of this rho p. And you can see that here we are looking at z and w being positive. So in particular, this quantity is negative. So it's well defined. We don't need any exponential moment or anything. And similarly, when p equal to 2, this term really vanishes, like p minus 2. So this actually goes to infinity, but this actually vanishes. So you won't get this behavior. And when p is between 1 and 2, we get a similar thing, just have to make sure that we kind of write it in the right form. But it's basically the same formula, just this will become 0 in the p equal to 2 case. Okay? So this is kind of under a minimal kind of technical assumption, one can actually show that limiting behavior for this log-partition function. Now I'll go back to p less than 1 case, because in that case, we need a different scaling. 1 over n is not the right scaling. Okay. So what this says is that, okay, so 1 over log-partition function has a non-trivial limit. And now one can try to understand, okay, whether this function has a unique maximizer. If yes, then what are the maximizing points and so on, which will give us a more result. Okay. Okay, and so this is for the general case. Now one can try to understand the behavior of this limiting partition function, but let's focus on the original model, the LP constraint model, because there one can explicitly write down things. So in the LP constraint case, if we go back to the original, our original problem, so there the beta CP actually is there. So which is, you can think about kind of the LP norm square divided by the variance, which is explicitly computable here. So for any p bigger than 1, if beta is less than beta c, then m sigma is indeed concentrated at 0, and one can prove a Gaussian behavior. So root n times the magnetization has a limiting normal with mean 0, appropriate variance. And if beta is bigger than beta c, then magnetization is not concentrated at 0. So that means there is a open neighborhood around 0 that the magnetization is outside, concentrated outside that open neighborhood. And if p is less than 1, then we need a different scaling. And in that case, what happens is that the measure is concentrated on 2 points. So if we look at sigma 1, sigma 2, sigma n, we can show that only 2 of them will be very big, the others will be very small, and one get a kind of a trivial result, like divided by. And you can see that this is much bigger than. So this scaling is actually more than 1 over n scaling, because p is strictly less than 1. So if p is equal to 1, then one gets back 1 over n. So right now we are missing p equal to 1 case. We have some partial result, but not the complete one. Okay. Now, one thing to see that if we take p equal to 2, we indeed get back beta c equal to 1. And if we take p equal to infinity, in the usual case, we get back also 1. But if p is going to infinity, this quantity actually converges to 3. So we have different behavior here. So if we look at beta c of 2, so this is indeed 1, beta c of infinity, which is also 1 because the variance is 1. But if we look at the limit of beta cp, one can check that this actually converges to 3 as p goes to infinity. So that means when p goes to infinity, something else is going on. But anyway, so this model can be explicitly kind of understood, and I just kind of write down kind of a simple kind of summary of this one. Okay. Okay. Any question before I go? So how to handle this kind of constraint behavior for this model?
So in the previous result, it was so there's no condition on beta. Right?
There is no condition on beta for any beta positive. Yeah. So this beta appears here. Yeah, beta appears here. So when we try to understand phase transition, then we have to analyze this function. If this function has a unique supremum, and that will give you beta less than beta c, and then multiple non-zero supremum, a non-zero optimizer, it will give you the other behavior. Yeah.
Thanks. Any other questions from the audience? Okay, please continue.
Yeah. Okay. Yeah. Please feel free to stop me if I am going too fast or anything is unclear. Okay. Okay. So let's try to go to the classical case. And now in the classical case, there are many different proofs, because now it's like, so let's focus on 3 different proofs. So the first one is based on large deviation, which actually involves this e to the power x square moment, or half Gaussian tail decay. But in the classical, Curie-Weiss is bounded, it's plus minus 1. So suppose I kind of try to fix the magnetization value equal to some constant m. Now the magnetization here is constant, is in the interval -1 to 1, because it's always average of plus minus 1. So in between plus. So m is in between plus minus 1. And we can see that the Hn of sigma, the magnetization, it's 1 over n summation sigma I sigma j. So if I simplify, this will be roughly half n times m square. So this m is the m of sigma. And one can explicitly compute the probability that in the classical Curie-Weiss model, what is the probability that my magnetization is exactly equal to m. So it's like because the Hamiltonian is a constant now, so it goes outside. And then we have to see what is the probability that summation of sigma I divided by n is equal to m. And that's an explicit computation using binomial probability. So that's explicitly computable. Now the binomial probability can be written as e to the power minus n times I, where I is kind of the rate function. And so in particular, if we try to understand the behavior of this measure, we have to understand when this function is minimized with respect to m. And if we look at this ix minus half beta x squared, so this will be minimized kind of the usual way. Take derivative, differentiate, and try to find all the solutions and check whether some solutions are minimum, some solutions are maximum, and so on. So here, if we kind of try to look at the function, the derivative is tan hyperbolic inverse minus beta x equal to 0. So that means the solutions are, they satisfy x equal to tan h beta x. So these are the solutions. And if beta is less than or equal to 1, there's only one solution, x equal to 0. So if we try to kind of write down the equation, if we plot the curve looks like this. So that should be 0. I think we need to tilt it. So 0 is the only solution. And one can then show that, okay, so the magnetization is concentrated around the 0. Whereas if beta is bigger than 1, then the solution is different. So in this case, we have this plus minus x star. And then one can show that the magnetization is concentrated around these 2 points. Okay, but here we really need this sub-Gaussian tail decay because we are using e to the power x square kind of properties. So this was the idea in Newman and Ellis and Newman paper to kind of to solve the model for general rho under this e to the power e to the power c times x square being finite assumption. Okay. Now there's a question. One can compute, yes, so that's what I'm trying to show in the next case. One can compute the asymptotic behavior of the magnetization as n goes to infinity. And remember that, as I mentioned in the classical case, so for beta less than beta c, the variance is this converges to 1 over, the variance of this converges to 1 over 1 minus beta square. And this is indeed the asymptotic variance.
So there is a question in the chat.
Okay.
Yes, I think he's he's addressing that question. Yeah. So I could read the question from the chat. He's asking, can you compute the variance of the fluctuation of the magnetization as n goes to infinity? This is from Yangri.
Yes. So here, this result actually can be written as, I mean, a consequence of this will be like if we look at the variance of m sigma. So this multiplied by n, actually this converges to 1 over 1 minus beta square for all beta less than 1 as n goes to infinity. And when the external field is non-zero, then okay, so then there is no explicit formula, but then also one can actually show that there is an asymptotic normal behavior. Yeah. So here we are focusing on h equal to 0, but for h, if h is non-zero, then one can get a similar equation. It will be x equal to tan hyperbolic beta x plus h, and then this has a unique solution. And then if h is non-zero, and then one can prove a Gaussian fluctuation there. Okay. Any other questions?
Thanks, Partha. Any other questions?
Okay. Now let me kind of show you one way to prove that Gaussian fluctuation. So I'm looking at the subcritical, the beta less than beta c case, but one can also focus on beta bigger than beta c, but then you have to concentrate around all those optimizers. So the second way to prove this kind of phase transition is using Stein's method for exchangeable pair approach. Now, I'm not going into the details, but the main idea is that if you have a standard normal random variable, then it satisfies this Gaussian integration by parts, right? If it is normal 0, 1, and if f is a nice function, say Lipschitz function, then expectation of x f x is equal to expectation of f prime x. Moreover, if this is approximately true, then one can actually also prove convergence to normal. Now, there are many different ways to prove this kind of behavior. One of the idea is this exchangeable pair approach. So where if you take one random variable and create a pair which is exchangeable, so that means the distributions are same even if you flip them. So W prime and W prime W, they have the same distribution. Moreover, the difference is very small in the following sense, that if you look at the conditional change, so look at the difference between W prime minus W given W. So this conditional change is linear with some lambda positive, but lambda is very small. So in this case, the lambda, think about lambda is very small, but strictly positive. Okay. So if this is true, and the conditional second moment is concentrated around this mean, now the mean can be explicitly computed. Using the exchangeable pair property, and it turns out that the variance is exactly, this expectation is exactly 2 times lambda times variance of W. Now, once this is true, then the science method actually shows that W divided by the standard deviation converges to normal 0, 1. So the heuristic idea is that, you can think about this is kind of a one-step discretization of Ornstein-Uhlenbeck process. So if you can create some exchangeable dynamics with a small linear change, and the quadratic, the second moment, conditional second moment is concentrated around the appropriate mean, then it has to be Gaussian. Now, in the Curie-Weiss case, one can actually look at the global dynamics. So the global dynamics is kind of defined for general Ising model. So in this case, the dynamics behaves like you choose one of the coordinate uniformly at random, and then change that particular spin value looking at the conditional distribution of the spin given the rest. So that's kind of the usual Hubbard dynamics. And the Hubbard dynamics actually is a reversible Markov chain. So actually it gives an exchangeable pair for the spin configuration. And one can explicitly compute the conditional change. So sigma is my original configuration, and using Hubbard dynamics, I create this sigma prime, look at the conditional change, and the change turns out to be like this. Now m sigma is very small because we have to magnify. So you can see that if beta is less than 1, so this quantity is concentrated around, okay, I think I missed a 1 minus here. So in this case, it will be concentrated around 1 minus beta over n times m sigma. And so this is true as long as beta is less than 1. And then the rest is a routine computation. Try to compute the second moment and show that it is concentrated. And then actually one gets the fact that m sigma divided by the standard deviation of the magnetization actually has a normal behavior. So that gives us another way. So if one can create some kind of exchangeable dynamics, and one can try to see that whether there is a linear behavior for this conditional change and some kind of concentration for the second moment of the conditional change, then that also gives another way of proving this normal behavior for the magnetization. And also critical, the variance also actually follows from this computation once actually if someone computes this one exactly. Okay, so that's another way. The third way is actually using the so-called Hubbard-Stratonovich transform. So this is actually nothing but the usual formula for a Gaussian moment generating function. So e to the power x square over 2, so this is nothing but the expectation of e to the power x times a standard normal. So here my eta is standard normal. And if we compute this exponential moment, we get e to the power x square over 2. Now this quantity, if I can expand it using an integral form, now using this formula in the classical case, one can actually linearize this the Hamiltonian in the following way. So for example, remember that we want to compute the asymptotic behavior of log-partition function, log z and beta. So log z and beta is the integral with respect to the discrete uniform measure of e to the power the Hamiltonian, beta times Hamiltonian. Now the Hamiltonian, Hn sigma, is exactly your minus Hamiltonian beta times, it looks like half times beta times n times m sigma square plus some constant, but the constant does not matter. And you can see that here we have this quantity like half times some constant times x square. So we can use this transform to linearize. Instead of m sigma square, we can write it as m sigma times a Gaussian. So I just have to replace x by m sigma. So we can do the same thing, but there is a 1 over n and all this quantity here. So if we simplify things, it will turn out that it will become this kind of integral. And this y is nothing but the Gaussian integral. And so this is exactly this y, right? Now, this is now better because there is no quadratic form. It's linear in summation sigma I, and this is nothing but expectation with respect to sigma I. So 1 over 2 to the power n sum over all possible sigma. So I can take this inside, and then e to the power this quantity is explicitly computable, and we can use the fact that expectation of e to the power some sigma times any constant x is cos-hyperbolic x. So this can actually give us an explicit formula. So that's another way. And if we want to understand the behavior of the log partition function divided by n, we can use Laplace's method. And so Laplace's method, actually, we have to look at the maximum behavior of the inside function divided by n, because this function grows linearly with n. So in particular, the log partition function divided by n converges to the maximum of the interior over n, or minus of infimum of y square over 2 minus the log cos hyperbolic root beta y, right? So that's another way. And one can actually easily also prove a Gaussian fluctuation. In this case, for beta less than 1, is if we look at W, which is the scale magnetization, this is 1 over root n. And if one tries to compute the expectation of e to the power TW, so both the numerator and denominator, because now remember, the numerator is coming because of the log partition of the partition function, and the numerator is coming because of this extra part. So one can actually compute it exactly and take the limit. And it turns out that the limit is given by e to the power t squared divided by some constant. And this is, you can see that this is actually a normal random variable moment generating function with mean 0 and variance 1 over 1 minus beta. So this also kind of gives you another way of proving this behavior. So the next question is, okay, so can we use a similar idea, one of these ideas? Now for the first one, which is using this last deviation, so there we need some more properties. We need exponential moment of x squared and so on. And this will work if we assume appropriate moment property for expectation of e to the power some constant times x and constant times x to the power p. Now, if I try to use Stein's method, this will be hard, because if we try to use Glauber dynamics, that's not easy to do here, because we are working on a constraint surface. So if we keep all the other coordinates fixed, then one coordinate can only change by a sign. So that's a big change, right? And the other part is here the change is discrete, because in the classical case, it's working on a discrete space, whereas in the LP constant case, we are working on a continuous surface. So the dynamics should be a continuous dynamics. So that means we have to figure out what should be the right dynamics. So what should be the right way to make a small change for the configuration staying on the surface, and so that we have a linear change, the conditional change is linear, and the conditional second moment is concentrated on the appropriate mean. Okay, so this is unknown. The second part is here in the Hubbard-Stratonovich transform, this is very much Gaussian. So, I mean, if we have some other polynomial part, this will not work. This is indeed Gaussian. So if you have any kind of scaling here, then this won't work. Okay. So here I'll focus on a version which is using a generalized Hubbard-Stratonovich transform. There is also a way to generalize the Stein's method, but I'll just focus on this part, because I think like this is kind of this I can do in the rest of the time period. So okay, so what is a generalized Hubbard-Stratonovich transform? So remember that here we are working on the self-scaled model. So for now, let's forget about this quantity, because this quantity is something which is negative, and if p is bigger than 2, this is also bounded. So we can just forget about this thing. So let's focus on this quantity. So this quantity is self-scaled. So we have numerator, and the numerator is just summation of sigma I, or xi in this case. And the denominator is 1 over n, but then this pn, which is summation of mod xi to the power p. Okay. So we need some way to linearize this quantity. So I mean, if we can linearize, then we can use Laplace's method and so on to simplify things, and probably we can do better. And this is the result, is that, yes, you can do that. So for any p bigger than or equal to 2, so p bigger than or equal to 2 is needed. So there exists a random variable u, which is nice in the sense it is positive, it's supported on 0 to infinity. It has density, positive density everywhere. One can explicitly write down the limiting behavior of the density around infinity and so on. But and this also depends on p. So the density, I should write u equal to up, such that one can linearize this e to the power x squared divided by y to the power 2 over p I mean, x and y at any non-negative constant in this way. So this expectation is with respect to u. So expectation of u of this integral over R. So when p equal to 2, so in that case, u is exactly equal to 1. And p equal to 2 case, we don't need any 2 over p. This becomes actually 1. And if you take u equal to 1, one actually gets back the usual Hubbard-Stratonovich transform. So a constant, u equal to constant, so you can directly linearize it. Whereas if p is strictly bigger than 2, then u is a proper random variable with nice behavior, with positive density, smooth enough density everywhere. Okay. Now, how does this help? So let's see. So how to use this? So fix p bigger than 2, p or p bigger than or equal to 2. And remember that our x is on rho p. Right now I'm focusing on the class on the rho p case, on the LP constant model. So suppose I take x from rho p and a Gaussian from Gaussian, eta from rho 2. So first, okay, so how do I simplify this? So here we are trying to linearize this quantity, e to the power x square over y to the power 2 over p. So let's try to use the standard Gaussian, standard Hubbard-Stratonovich transform. So we can look at the square root, put a Gaussian, and put a square root of 2. So this is the usual Hubbard-Stratonovich transform. Now, if we can write a Gaussian random variable as a product of two independent random variables, x and u, where x satisfies this property and u is independent of x, then I can replace eta by this x times u, and x has density e to the power minus x to the power p over p, put it there, and do a change of variable, multiply z by y to the power 1 over p, and then you can see that you get this integral. Now, this is almost linear except for this y to the power, but that's a polynomial term, right? So this will linearize this quantity. So as long as we can show this existence of u such that any Gaussian random variable can be decomposed as product of two independent random variables, one is this u, the other is coming from rho p. And we need to do it for every p bigger than 2. Now, one might say like, okay, so why? Okay, so let's kind of show that how this can be useful. So, okay, so here is kind of a small one. So here first, let's kind of try to put this polynomial term, because Tn over n will be concentrated and it really does not matter in our case. Let's also forget the other minus part, like that was also for p bigger than 2 as an order 1 term. So let's focus on the dominating term. So this is the term we need to understand. So you can see that here, if we put u just using our previous analysis, we can linearize it. So remember here, this is x, this is x, this is y divided by y to the power 2 over p, and this is y. So it's exactly the same. Now x is Sn, y is Tn, and everything is just a constant. So we can write it expectation with respect to this Sn and Tn, but now these two are linear because Sn is summation xi, Tn is summation mod xi to the power p. So if I take the sum outside as a product and take the expectation with, so this expectation is with respect to everything. So this is with respect to u, with respect to x1, x2, xn. And you can see that if we take the expectation, so there should be two expectations here. So expectation with respect to u, and this is with respect to x. And you can see that all these x1, x2, xn, as long as given u, this will just give you, so here we have this whole to the power n because x1, x2, xn are IID. And now I can actually use, but now this is actually an expectation with respect to u. So we can still need to do some more work, but one can try to understand the log-partition function behavior by using appropriate properties of this u. So this is the first step. If u is equal to a constant, then we don't have any expectation here, then we get back our original classical result. But now we have this u1. Okay, so the question is, okay, so how to show that this u exists? So that actually follows from a particular coupling. I'll not go into the details, but this says the following. So the main behavior, the main thing to know is the following, that if you have xp from the rho p density, if you take the pth power of the absolute value divided by p, it has a gamma distribution. So we really want to do a coupling of this gamma distribution. And the main theorem which we prove is, which is very technical, is that there exists an additive process. So additive process means increments are independent, such that, first of all, y0 has a distribution given by minus of exponential, and yt has a distribution given by t times log of gamma t. So in particular, if we look at e to the power yt will have this kind of rho p distribution. So to create that u, what we did is we just look at u given by the difference of this y at 1 over p and 1 over q. So this u will be the y at the point, it will be the e to the power of that. So it's like exponential of y at the point 1 over p, 1 over q minus y 1 over p. So if we take this as our u, then we actually have the relation that we want, and q is equal to q will be equal to 2 in the Gaussian case. But this is much more general. So because if we take q equal to 2, x2 is nothing but Gaussian, and if p is bigger than 2, this will actually give us the corresponding result. Now, in general, u does not have explicit description. It exists. It's an existential proof. We have using some limiting behavior. But in some cases, one can compute the density. So actually, there is one such case, which is when p is equal to 4. So u42, for example, one can compute the density, but in the other cases, there is no such density. So it actually shows the existence of this model. Okay. Now the proof is actually, I mean, we right now we don't have any geometric interpretation like what is going on. This is more like a kind of a hands-on construction, a coupling construction of all this log gamma distribution. So yt has a constant times a log gamma distribution. So this is a coupling of the log gamma, and using which one can prove this behavior. Okay. Now, so there are other results actually one can do. So here I just focused on the generalized Hubbard-Stratonovich transformation, but a similar thing can also be used to create an exchangeable dynamics to use times method. So the main idea is, instead of working on the surface of the sphere, go to the Rn case, do some change there, and then project it back and show that it is indeed an exchangeable dynamics satisfying conditional change being linear, and then use that to prove a Gaussian result and rate of convergence. But even using the Hubbard-Stratonovich transform, one can also prove a Gaussian convergence exactly in the classical case. So for example, one can exactly show that similar to the classical case, one can compute this limiting behavior and show that it indeed has a limit given by e to the power t squared times some constant. That also proves the Gaussian behavior and so on. So there are multiple ways to kind of generalize these things. Now, this can also be used to analyze the critical behavior at beta equal to beta c to show n to the power 1/4 times magnetization, the scaling behavior, but which is more technical. And this method can also be generalized to in the high dimensional Curie-Weiss. So instead of supported on R, it's more vector valued, and instead of summation sigma I square, it will be summation, say, sigma I transpose sigma I. So because it can be done. Okay, so there's a question. The rate of convergence. No, the total variation distance, in the classical case, the total variation distance cannot be done because the original model is discrete. And the rate of convergence in the Wasserstein distance is 1 over root n. In the Kolmogorov-Smirnov distance is also 1 over root n. And actually, one can actually get a lower bound also in this case, in the classical Curie-Weiss case. But in the P finite case, because we are working on the continuous model, probably something can be done for the total variation distance, but that's very strong. So what we can do in Wasserstein distance and some on the Kolmogorov-Smirnov distance, but not in total variation distance. Okay. Okay. Okay, now there are many questions. The first question that is, what is the geometric interpretation of this generalized GHS transform? the reason is that our construction is kind of completely hands-on construction. And now using that construction, one can actually create a coupling of a uniform point on the LP sphere. So take any p from 2 to infinity, and using this, we can create a coupling of all these points such that at every p, it is uniform on the LP sphere, but otherwise the continuous change. So now we have a continuous way of like deforming all these things. So is there any way to kind of explain this geometrically? Now this actually, we know how to calculate one constant, but what about multiple constants? Because if we have multiple constants, I mean, we cannot ignore it. I mean, here by scaling, we remove the constraint and then work with the self-scaled or the self-normalized version. If we try to handle multiple one, we need different idea. Now the question is, what happens for beta bigger than beta c? So right now, what we can prove, okay, so that should be beta. Right now, we can prove that if beta is bigger than beta c, the optimizer is away from 0. So there is an open set around 0 such that the optimizer is out of that set. But we really don't know whether it's concentrated on exactly 2 points modulo sign symmetry. And also, what about general constant, in the sense not summation xi to the power p equal to constant, but some other constant, even some nonlinear constant? Then what happens? And the starting question for us was trying to understand the disordered spin-glass model. So the next question is, can anything be said about the disordered model? Like, for example, if there is also a phase transition at some beta c, depending on the disorder, which is different from the non-disordered case. So if beta is less than beta c, can one say anything about the fluctuation results for the overlap or for the log-partition function, which is kind of a more like a harder version? Okay. Okay, so I'll stop here. Thank you. If you have any questions, please ask them. Thanks very much.
Thanks, Partha, for a very interesting and clear talk. Are there questions from the audience?
Did you consider dynamical problems in the case in which you have phase transition?
We haven't considered, but that's one of the plans. I think so. We kind of here to try to understand the geometric interpretation. We are trying to see like whether we can make kind of a dynamical version, both in terms of the dynamics, like fix p, and also change the p and try to see what is happening. Yeah, but that's also some other ongoing project. But yeah.
Thanks.
And the other question is like, when p goes to infinity, then what is happening there? Because there is a difference. It's not beta. The beta c is going to some other constant like 3 instead of 1. So trying to understand that behavior.
Thanks.
What's going on there? Some mass is being lost or something, or something? Why is? Do you have some interpretation for why it goes to 3, not 1?
Yeah, so I think what is happening is that when you take p going to infinity, there's a difference between working with summation mod xi to the power p equal to n, or this to the power 1 over p equal to 1. Now, if you consider this restriction, this will actually give you the max of mod xi equal to 1, right? I mean, when p goes to infinity. So in this case, one can try to see that probably when p goes to infinity, just on a single constraint, the model behaves not plus minus 1, but uniform between plus minus 1. So the continuous uniform between -1 to 1. And in that case, the variance is 3 or 1/3, and the inverse of the variance is 3. So if you directly take the limit, that actually is happening. So the uniform distribution is giving the typical behavior, not the extreme point. But so so if we have some multiple constant, probably that will enforce it to kind of focus on the not on the interior but on the vertices. Yeah.
I see. Any other questions from the audience? Well, if not, then let's thank Partha for a very interesting talk and nice results.
Okay, thank you.
Okay, so we'll close and see everybody next week.
Okay, bye.